Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my next video in my long series I'm doing on the Math Lovers book. For those of you just joining me, I have a 3-volume series that's available on Amazon.com called the Math Lovers book. They're available either in paperback or in Kindle, and you can search for it using either the title, The Math Lovers book, or my name, David Tare. Anyway, you might want to check it out. I think you'll enjoy it. But, even if you don't decide to buy it, you can still enjoy my free lectures on this series. And I'm still doing volume 1 of this series. I'm up to chapter 2, section 2.4, which is on the least common multiple. I just started talking about the greatest common divisor. I just wrapped that up yesterday. Anyway, let's begin. So, what is the least common multiple, also abbreviated as LCM? Well, it's very closely related to the greatest common divisor, GCD. And just like it says, if you have a list of numbers, which I think I call N1 up to NK here, the least common multiple of those numbers is just what it says. It's the smallest number that's a multiple of every number on your list. And, so that's pretty straightforward definition. And I think it's just worthwhile to look at some examples. There is an algorithm for computing the LCM that's analogous to the first algorithm I showed you for computing the GCD. I don't know if you guys remember what we did last time, but with the GCD, we took the prime factorization of each number on the list, and then we used the minimum exponent for all the numbers for each prime factor. We could do the same thing with LCM. The only difference is instead of using the minimum, we use the maximum. So same idea. So let's do some examples. Suppose we wanted to compute the LCM of 8 and 10. Well, you can start by doing the prime factorization of both 8 and 10. 8 is 2 cubed, and 10 is 2 times 5. So you go through each prime divisor, and the maximum exponent multiplying 2 is 3 in this case, 2 cubed. So we know that 2 cubed has to be a factor of the LCM. And similarly, since 5 is a divisor of 10 in this case, we have to include, what another difference is that in the case of LCM, we have to include all the prime divisors, not just the ones that only appear in each number, but in any number. So since 5 appears in the prime factorization of 10, we still have to include it. And since 5 appears with exponent 1, we have to multiply a result by 5. So that gives you 2 cubed times 5, or 8 times 5, 40. So that's the answer. The LCM of 8 and 10 is 40. Let's do a second example. How about the LCM of 18 and 24? Same idea. You do the prime factorizations of 18 and 24. So 18 is 2 times 3 squared, and 24 is 2 cubed times 3. So you just go through each of the prime divisors. In this case, there's only 2 of them, 2 and 3, and you look for the maximum exponent. And since the maximum exponent of 2 is 3, that appears in the prime factorization of 24. We have 2 cubed, and then for 3, we have 3 squared because that's the maximum exponent of 3, which appears in the prime factorization of 18. So when we collect those terms, we get 2 cubed times 3 squared, or 8 times 9, or 72. So the LCM of 18 and 24 is 72. Pretty straightforward, I'd say. Let's do a third example. How about the LCM of 60 and 108? And just like the case with GCDs, these got harder and harder the larger the numbers get. And this method does become impractical when the numbers are super large. Like I'm talking 100 digits or more, because for a lot of those kind of numbers, it's hard, if not impossible, to find prime factorization. But there is another method, which I'll get to at the end of this lesson. Anyway, let's just keep using this method. So to get the LCM of 60 and 108, first we do the prime factorization of 60, which is 2 squared times 3 times 5. And then 108, we have 2 times 3 cubed. Is that right? Oh, 2 squared times 3 cubed, I'm sorry. So, and then we do the same thing. This time we have 3 prime divisors, 2, 3, and 5. Or no, yeah, 2, 3, and 5. So the maximum exponent multiplying 2 is 2. 2 squared, which occurs in the prime. Well, it occurs in both of them, actually, both 60 and 108. So we have to have 2 squared in there. And then for 3, we have 3 to the first, and the prime factorization is 60, and we have 3 cubed, and the prime factorization is 108, so we have to include 3 cubed. And then for 5, we have 5 on the prime factor of 60, not on the prime factor of 108, but we still have to include it since we include all the prime divisors. So we're going to get another factor of 5. When we collect all these terms, we get 2 squared times 3 cubed times 5. 2 squared is 4. 3 cubed is 27. 4 times 27 is 108. We still have to multiply by 5. That's going to give us 540. So the LCM of 60 and 108 is 540. Pretty straightforward. Like I said, I think the hardest thing about applying this algorithm is doing the prime factorizations. But once you have them, it's very easy. And you can do the same thing with more than two numbers. Here's a couple examples where we have more than two numbers. How about the LCM of 5, 6, and 7? Same idea. We do the prime factorizations of 5, 6, and 7 first. 5 and 7 are already prime, so we don't have to factor those. 6 is 2 times 3. So when we do the LCM, we have to include all those prime divisors. So we get 2 times 3 times 5 times 7, which turns out to be 210. So that's the LCM of 5, 6, and 7, 210. How about 5, 6, and 8? Well, same idea. 5 we already got. That was for prime, so prime factorization of 5 is 5. 6 we did already as well. That's 2 times 3. 8 is 2 cubed. So this time there's only 3 prime divisors. We have 2 cubed. That's the highest power of 2 in our the numbers we started with. And then for 3, we just have 3 to the first because that's what appeared in prime factorization of 6. And then for 5, we just have a single factor of 5. So we get 2 cubed times 3 times 5, which is 8 times 15 or 120. So that's how you do that. Pretty straightforward. And just one more example I'm going to go over. This is probably the hardest one. How about the LCM of 60, 80, and 100? Same idea. Prime factorization of each number. Prime factorization of 60, we already saw that one. It's 2 squared times 3 times 5. 80 is 2 to the 4th times 5. And 100 is 2 squared times 5 squared. So when we collect all the factors, we're going to get 2 to the 4th because that's the highest power of 2 and the prime factorization of each of these three numbers. And then we get a single factor of 3 because 3 appears in the prime factorization of 60. And then we get 5 squared because that's the highest power of 5, which appears in the prime factorization of 100. So when we're done, we get 2 to the 4th times 3 times 5 squared. And if you work this out, it turns out to be 1200. So the LCM of 60, 80, and 100 is 1200. That's how you do that. Pretty straightforward. And the last thing I'm going to say in this lecture is that there's another method which is actually much more efficient, especially if you're working with large numbers. And if you're writing a computer code to do this, this is the way to do it. There's actually a formula for the LCM of two numbers in terms of the GCD. This is a very useful formula. It turns out that for any two integers a and b, the LCM of a and b is equal to the product, a times b, divided by the GCD of a and b. That's a very useful formula. And so once you know how to compute the GCD of two numbers, you can automatically compute the LCM. Well, what about three or more numbers? Well, then you have to do it recursively. Remember what I said in my, I think a couple lectures ago when I was talking about the GCD of more than two numbers? You can only, you do it two at a time. It's the same idea. It's recursive. So the LCM of three numbers, A, B, and C, is equal to the LCM of A and B and C. Or if you like, it's usually better to start with the biggest numbers first. So you would first calculate the LCM of A and B. It might be actually easier in the LCM case to start with the smallest ones first. but it doesn't really matter which ones you start with. That's how you do it. And to do the LCM of two numbers, I mean, you still have to compute the GCD, but we could use the Euclidean algorithm if we like to compute the GCD, and that's like I said in my last lecture. That's a lot more efficient than using the prime factorization. So there's no need to compute any prime factorizations when you're computing GCDs or LCMs. You can just use the Euclidean algorithm as kind of the basic operation, and then you can just use recursion if you want to get the GCD or the LCM of more than two numbers. So that's how you can be that. That kind of summarizes how you compute GCDs and LCMs. I have a lot more examples of this in my problems and solutions manual. And maybe what I'll do, I have been going over the problems and solutions. I think what I need to do is I have to, maybe I should start presenting some problems and give you guys a chance to work on them, and then present, do another video or present the solutions, or maybe I could do live streaming of this. I haven't figured out how to do this yet. Maybe you guys can leave comments and let me know what you prefer. But anyway, this is another feature I think I'm going to add to this channel because I would like you guys to participate. I would like you guys to try to do some of this stuff I'm teaching in this book. So anyway, that concludes my lesson for today on the least common multiple. I think it also wraps up everything I'm going to say about the LCM. So thank you for watching. Long live math, and I'll see you guys next time. Bye.